Fluid motion is governed by the Navier-Stokes equations, named for Claude-Louis Navier, an early 19th century French physicist, and George Stokes, a 19th century British physicist. They represent the application of Newton's laws of motion, in particular Newton's second law, which is force equals mass times acceleration, to fluid flow. The first two equations, for the 2D case, there are three for the 3D case, are called momentum equations, and they are derived directly from Newton's second law of motion. The third equation is called the continuity equation and holds for incompressible fluids only, and we will only consider incompressible fluids, like water. The variables and parameters are ρ, representing fluid density, u and v, representing fluid velocity in the x and y directions, p, representing hydrostatic fluid pressure, and mu, the viscosity coefficient. The physics required to derive the Navier-Stokes equations is, first, Newton's second law of motion, second, Reynolds' transport theorem, which we'll get to shortly, and third, Newton's law of viscosity, which we'll get to in the next vid. Normally, Newton's laws of motion apply to solid objects, so how can they be applied to fluids? That is the question. We will apply Newton's laws to a control volume that is fixed in space. When the fluid is in motion, the fluid molecules are flowing in and out of the control volume continuously, while the control volume, a mathematical construct, remains fixed in space. The diagram shows a 3D volume, that is a cube, and we will be using 2D control volumes, that is squares. The Reynolds transport theorem allows us to apply Newton's laws to the control volume, which is fixed in space. But first we'll look at the continuity equation, because it's the easiest to demonstrate, and we'll reuse parts of the demonstration in what follows. The continuity equation states that the partial derivative of u, the x velocity, with respect to x, plus the partial derivative of v, the y velocity, with respect to y, equals 0. And it's demonstrated by examining the fluid flow into a small control volume centered at x and y. What is the rate of fluid flow into the control volume through side A? The fluid velocity at the middle of side A is u evaluated at x minus dx over 2, comma y. So the rate of flow into the control volume, that is the volume of fluid flowing through side A, is u of x minus dx over 2, comma y times dy. Note that the y velocity does not contribute to fluid flowing through side A. On side B, u of x plus dx over 2, comma y is the velocity of fluid flowing out of the control volume. So the rate of fluid flowing into the control volume through side B is minus u of x plus dx over 2, comma y times dy. Similarly, the rate of fluid flow into the control volume through side C is v evaluated at x, comma y minus dy over 2 times dx. And the rate of fluid flowing into the control volume through side D is minus v of x, comma y plus dy over 2 times dx. Note that since the fluid is incompressible, the total rate of fluid flowing into the control volume must be 0. So the sum of the flow rates through each side is 0. Dividing the total flow into the control volume by the volume of the control volume gives equation 1, which can be arranged to equation 2, and taking the limit as dx approaches 0 and dy approaches 0 gives the continuity equation. Newton's second law of motion is force equals mass times acceleration, and it can be written as the rate of change of momentum, that is the rate of change of mass times velocity, equals force. Newton's laws apply to objects that accelerate when a force is applied. We want to apply them to a control volume that is fixed in space and which fluid is flowing in and out of. Reynolds' transport theorem to the rescue. It states that the rate of change of momentum of a fluid in a fixed control volume equals the force applied to the control volume plus the rate of momentum flow into the control volume. We'll divide the terms in the Reynolds transport theorem by the volume of the control volume and then take the limit as the control volume shrinks to 0. The result will be the Navier-Stokes equations. Now we'll go through the terms in the Reynolds transport theorem one by one. The first term is the rate of change of momentum of the fluid in the control volume. The x momentum of the fluid in the control volume is the mass of the fluid times its x direction velocity. That is rho times v times u, where rho is the density of the fluid, v is the volume of the control volume, and u is the x direction velocity of the fluid at the point x comma y in the center of the control volume. Dividing by v, the x momentum per unit volume is given by rho times u, and its rate of change is rho times the derivative of u with respect to time. The second term is the flow rate of momentum into the control volume. We start with the fluid flow rates into the control volume through each side. We've seen this diagram before. If we multiply the fluid flow rate by the fluid density rho, we have the mass flow rates into the control volume through each side. And if we multiply the mass flow rate through side A with the x velocity at the center of side A, we have the x momentum flow rate through side A. And similarly for sides B, C, and D. The expression at the bottom of the page is the total x momentum flow rate into the control volume formed by summing the flow rates through each side. The first equation is the total momentum flow rate into the control volume from the previous slide, divided by the volume of the control volume, that is dx times dy. As promised, we take the limit as dx and dy approach 0, giving equation 2. Using the product rule for differentiation, one of the few times we use analytic calculus, we take the derivatives indicated in equation 2, yielding equation 3. Simplifying equation 3 and using the continuity equation as indicated, we have equation 4, which is our goal. Recapping, we have the Reynolds transport theorem, which states that the rate of change of momentum of the fluid in the control volume equals the force acting on the control volume plus the flow rate of momentum into the control volume. We have shown that the rate of change of the x momentum in the control volume per unit volume equals rho times the partial derivative of u with respect to t. And we have shown that the flow rate of x momentum into the control volume per unit volume equals minus rho times u times the partial derivative of u with respect to x plus v times the partial derivative of u with respect to y. So if we bring the x momentum flow rate term to the left side of the equation, we have equation 1, and using the same derivation for the y momentum, we have equation 2. So the good news is that we have derived the left sides of the momentum equations. The bad news, the left-hand side is the easy side. The assignment is to review the derivations of the continuity equation and the left-hand sides of the momentum equations.